All right. Welcome to January 29th, Data Structures. So here's what we're going to do today. I'm first going to talk about a tip of the day. I forgot to do the tip of the day last time. I'm going to do a tip of the day. I'm going to do Lab 1 post-mortem without the little H on there. Not sure why that's there, but I know how to fix that. There we go. All right, we're going to do a Lab 1 post-mortem. Hopefully all you guys finished the lab to the extent that you showed progress on it. And I'll explain what I mean by that in a little minute, in a minute. And then we're going to talk about this idea that we discussed a little bit the other day about references versus pointers and this idea of passing something to a function by value. Okay, so we're going to go into it, dig a little bit deeper there, and I'm going to show you exactly what that means in terms of what you think you're doing to some data may not be exactly what it is, and we'll figure out how to rectify that if that's the case. Then we will go into this idea of doubly linked lists. Instead of last time we did singly linked lists, and this time we're going to do doubly linked lists, and hopefully we'll get through there. Once again, the benefit of being the afternoon class is that I did something this morning, and the board was like just completely jumbled up again. So we'll try to avoid that. It'll still be somewhat jumbled up, but I'm going to try to use some colored chalk. I got a great suggestion from one of the students saying, next time try colored chalk. So I will. We'll see how that works. But anyway, it should be an interesting conversation, I hope. And then we'll just finish up talking about what a circular list might be. OK? All right. Any questions administratively before I actually get going? No? OK. All right. So here's the Unix tip of the day. This is a command that could possibly be the only command you actually need to know in Linux. If you forget all the other commands and you know this one, you will actually be OK. It's called the man command. And that's not a sexist command. It means manual, right? And it tells you how to use a command. OK? So it actually describes what you need to do to use the command. So for instance, if we go over here, and let's see if I can do this without, there we go. All right, almost big enough. There we go. OK, so if we do something like man and then ls, which is the ls command, OK, it will give you the following. It does a nice little less file here for you. And it tells you what the command is. By the way, I fixed my pointer. Hopefully the batteries won't die today on the green pointer. It tells you what the command does, and then it gives you a little synopsis. Now, look, nobody in the entire history of the world has ever memorized all of these flags for ls, right? You can type in pretty much any letter, and it will do something, right, for ls. So you don't have to memorize these things. But if you want to figure out what some of these flags do, keep looking. There's a description here, and then we go down, and then da-da-da-da. Here, now it tells you what all the flags do. OK, so if you happen to type the -1 flag, it says the numeric digit 1. It says force the output to be 1 entry per line, which means you'll get file, 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 instead of kind of a list going sideways as well. OK, so that's nice. There's list all entries except for this crazy dot and dot dot directory, et cetera. And so there's a zillion different flags, and this tells you what all of them do. OK? Some people have written their manual pages to be to actually give examples at the bottom too. I'm not sure that ls does, but you can. It just gives lots and lots of information about this. OK, so you can do that for any command, right? Oh, here's some examples. Let's see. Following is how to do an ls listing sorted by increasing size, right? All files, reverse it, order by size, so it actually orders it by increasing size. OK, and it tells you a little more about it. So this is the way to get the information about that command that you have no idea how it actually works. Let's say you were looking for a command to do some searches. Well, man search probably won't give you anything, right? Because there is no command called search. But if you do man-k for keyword and then type search, it gives you a whole bunch of different things, right? And if you look through some of these things, that's actually a lot of stuff. That was probably not a very good example. But there you go. The one we used before, this one called grep, is in there, right? And it says file pattern searcher or something like that, right? So it'll tell you, hey, there's how I go and search for my file. And then you type q to get out of this. You type man grep, and it tells you how to use all these different types of grep through the files. And again, a zillion different flags, but you can, you'll slowly learn how to use some of those. Okay, so the key is man, and then space, and then the name of the command, and you'll find out all you need to know. If you don't get enough examples, just go Google it. I mean, that's what everybody else does. So, for what it's worth. OK, questions on man. All right, that was our Unix tip of the day. OK. All right, so hookbook. All right, for the most part, good job overall. OK, great job on like trying to understand this problem that was a little bit tricky. I mean, having linked lists inside, dynamic arrays inside of dynamic arrays is not necessarily the easiest thing to understand, especially when you're trying to say, what part do I expand, and how do I do the expansion, and so forth. But overall, pretty good. Look, I understand it's difficult to write code in a fixed, short, given section of time, especially if it's like an hour, right? That's not enough time to really, for lots of people, that's not enough time to just write the functions to get your head wrapped around it, because you'll have some bug and you'll have some other issue you don't quite understand, and then you get a seg fault and blah, 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 right? So that happens, and I understand it. The point of the labs is, A, to get a smaller setting where you get the chance to sit in front of a computer and do your thing, right? And you can ask a question to one of the 3 TAs in the room, or the instructor in the room, and you can actually get some good information out of that. So that's part of the purpose of lab. The other part is to actually work on a problem in real time and try to understand it. The purpose of the lab is not to grade you on your lab results. Okay? I mean, we're going to look at them, and we want to look at them. We want to make sure that you're trying and that you're attempting to do these things. But if you end up getting to the end of the lab and can't, it's not working and it's seg faults, don't panic, and don't go home and spend another 6 hours trying to work on it. So provide what you have, and then if you want extra help on it, come to an office hours at some point. Okay? Does that make sense to everybody? I mean, I hope that's I don't want to make the lab should not be a stressful time. The lab should be like a learning environment, and that's what I want you to make sure you understand. Okay. You do have to keep track of some of the details with this hookbook thing. Like I said, I mean, there's dynamic arrays inside of dynamic arrays, and you've got an array index you have to keep kind of passing through, and then you've got another array, and you've got the structure. I mean, there's a lot of details just in that one little fairly straightforward method that you had. Okay, go to office hours. Let me show you before I even do that, the trickiest part I think that people had was this expanding of the dynamic array. Okay, you got to a point where you said, all right, I need to expand this array, and how do I do it? And then whenever we looked at your code, we looked at it, and there was like something was missing, and that was what was causing this little issue. And there's 5 things you actually need to do. I went over this in the labs I taught. There's 5 things you need to do when you're expanding your dynamic array, right? The first thing you need to do, and I'll show you the actual code that I wrote that does this, and like most of you guys got a very similar looking code. Okay? First, you need to create the new temporary array. Why? Because you've got an array this long, and you're trying to make an array twice as long, and that's a whole other piece of memory. So you need to make that new piece of memory, usually request that new piece of memory from the operating system, and it's bigger, but it doesn't have anything in it yet. Okay, that's the first thing you do. Then you have to copy copy all the items. So you have this array. You have to copy all those items one by one into the new array. You have to do that. Otherwise, you'll just have a blank array, and then all the stuff that you did would have been lost. So you copy that in there, and that takes a loop, right? There is a function called copy. If you want to look it up, you can use it. You just have to just document it, right? That's what you're doing. It will copy for you, but it's just a loop. I mean, it's exactly what you would write, a little tiny loop that copies one element at a time. Then you need to delete the old array. If you don't do this step, it's not the end of the world. Your program will probably continue running, okay? Because if you don't delete the old array, it just sits around in memory and wastes memory, but it's not affecting anything else. Okay? It's not good practice to not delete it, but that's probably not the end of the world. Okay, this one would be the end of the world. If you forget to set the old array pointer to point to that new one that you've created, after you delete it, or even if you don't delete it, you're not going to get the new data that you actually asked for, or the new size of the array that you asked for. It's going to be the wrong size. And then finally, the 5th thing you need to do is you need to update that capacity of the structure. When you set, you'd think that computers are smart enough, right? If I ask for a piece this big, well, the rest of my program will all of a sudden know it was this big. That's not the way it works, okay? Your program right now knows that your array is this big. You've asked for more space that's this big, but you got to tell your program. In fact, in this case, it was the friend capacity. You have to tell the program, oh, now my capacity is actually this much bigger. Otherwise, we'll just kind of keep in a never-ending loop, and you won't actually increase the capacity, and it will not let your program run correctly. Okay, those are the 5 things you need to do. Let me show you how I did it. Okay, and I've done this. We'll do this a lot during this class. You'll see a lot of code. Reading code in class, I understand, is also not the easiest thing in the world, but we'll try to go slow enough that you'll get it. First of all, I picked I as the pirate index. Remember, we've got all these pirates we're going down, and one of them is the one we're looking for. Okay, and that one, as we scanned down in our first loop, we ended up with a pirate 3 or whatever it was. That's what this I stands for. I probably should have named it a better variable. Try to name your variable something that makes sense. In this case, an index works all right. I works all right. OK, then this is the new part. I'm creating my new integer array that's this capacity. And this, again, this stands for, this is the hook book we're talking about. This is the index of the exact pirate we're looking at. And then the capacity, and I'm multiplying by 2 to make it twice as big. This is the copy part. Okay? I picked a different variable. If you picked I, you'd be in trouble, because then you'd have an I here and another I for the copy count, and it would not work. You have to have a different variable in 2 different loops if they're inside each other. That's just the way it goes. Right? And then I did my copy, and what I'm doing is I'm saying, put the new value into the temporary array at that index from the same index value of the old friend list. That's the copy part. Then I go ahead and I delete the friend list. You should have this bracket here to say delete the whole array. And this does not delete the variable friend list. It deletes what it's pointing to. That's the way delete works. Which means that on the next line you can say set the friend list to be equal to that one you just created. All right, that's the big part right there, setting it to what you equal or what you just created. And then finally, increase your capacity. Okay, increase the capacity. Does this make sense to people who might have had a little bit of a mistake? And if you want, go back to your code. If you still had mistakes in it, I'll bet 9 times out of 10, this is where that some mistake was made in there. Okay, question on it? Yes.
At this point, would temp still refer to that friend list?
Sure. At this point, temp still refers to the same thing. So what you've said here is your friend list now equals temp. They're exactly pointing to the same thing. But when your function ends, and I don't actually have the end of the function here. When your function ends, then temp goes away. So, but you don't care about it anymore because you might, you'll create another temp later when you want to create a new array again. Yeah, good question. Yes.
So for this, I think that you need to pass the parent.
Yes. So this is not the whole function, the whole method we were doing. This is part of this. I actually had a little loop that was going through going, is this the right pirate by member ID? Is this the right one? Is this when I got to the one that was the right one, I equaled that pirate name or that pirate index. That was what it was. Yeah. Good. Yes.
So this code is in the add friend function, right?
This is in the add friend function. Yes, part of it. Yeah.
Can we do it separate?
Yeah, sure. So a number of you did. You said, I want to do another function or another method that's just this section. That's fine. You can do that. You have to pass along a couple things, right? What are you going to need? You're going to need to pass along the index for the pirate, right? And you are probably, let's see. I think that's all you absolutely need to pass in, is that, right? And you need to return, well, let's see. I think that's it. You might actually have to pass the hbook in, right? You probably have to pass the hbook as well. Yep. You don't have to pass the friend capacity if you've got the hookbook pointer, because then you can get to it through this. Yeah, you can do that. The other, you could pass just the pirate pointer if you wanted to. You could pass just hookbook I, and then whatever you pass that in, that would be you'd be able to use that to do the rest of it too. So there's a number of different ways, but you could do that. This is such a short function, really, that it's not necessary. But you could have done that. And I saw some good examples of people doing that. Yeah, question. You had a question.
Yeah, I don't quite understand the purpose of the last line because it seems like you already multiplied.
Right. Good point. OK. So I mentioned this a little bit earlier, but here's the deal. Up here, you're using the friend capacity times 2 to say, I need a new array that's that big, right? Does that actually change the friend capacity by saying times 2? It's just asking for that size, right?
Okay.
Right. It's like if you said A equals B times 2, right? does that mean B is now twice as big? No, that means that A is twice as big as B, right? So that's all that means there. And that was what a couple people, didn't quite get, which is fine. All right. Any other questions on this? All right. Good job on the homework. That was excellent. Okay. All right. Let's see. That was not. I'm going to actually take that out. This was not a page from last. There we go. All right. Okay. So the next thing I want to talk about, we mentioned it the other day in class. I'm gonna hammer it a little bit more so that you kind of see an actual example of what this is all about. Remember how I said, and I should do a little caveat here. Unfortunately, C++, this is on video, I guess. I shouldn't say it too loud. Somebody might listen. But unfortunately, C++ has some syntax choices that I don't think are very easy to understand. Okay? They've used this to mean kind of two different things. Okay? When you declare a function, and you say some type with this ampersand in here, okay, that means I am going to pass you a variable and you get to treat it as what we call a reference. Okay? You actually, when you're calling the function, you don't use this, which you do in pointers, so it gets very confusing. You just have to kind of figure it out and go with it. But what this means is you get to pass in this variable, A in this case, and you're going to be able to change it, and that change will be reflected in whatever you called that function from. Okay? So I'll show you the example so you'll see what it means. But basically it's saying if you change A and B, the original calling function sees that change as well. That's not normally the case. Here is when it's not normally the case. And this is what we do all the time, right? We say, here's our swap function. And by the way, a swap function in this case is taking two variables and swapping their values. So if A is 2 and B is 5, after I do the swap function, we want A to be 5 and B to be 2. We want to actually swap their values. Fair enough? OK. I'll show you the actual code for that in a sec. Now, in this case, if you just pass in, if you say, I'm going to give you, I want a function called swap that gets A and B as integers, what's going to happen is, like I mentioned the other day, the compiler will say, OK, here's two copies of A and B. Right? The copies are what you get to do your stuff on. And whatever you do your stuff on, you can change A and B all you want. When the original function gets back, all it's going to see are the original A and B's. It's like all that is wasted. Right? But it's not wasted because you can use that to your advantage if you want to change these inside the function. It just means the calling function doesn't get to see those changes. That's fine. But that's the way it works this way. Now, there is a third method. Okay? There's a third method that looks like this. You could say, all right, I'm going to do my swap, and I'm going to give you a pointer to A. In other words, the address where A, the variable, resides. And I'm going to give you a pointer to B, where B resides. Okay? And then I'm going to do my function. Now, if you refer to the pointer A in your function, it will actually go to that address, change that value, and then the original calling function will again see that value. Okay? The syntax is a little bit different in this, which I'll show you as well. But this is another way to do it. This is the way we would do it in C versus C++. The reason we have references in C++, some things are actually a little more clear, and it's a little more safe in terms of you can't do as much to harm the surrounding memory with these references as you can with pointers. You can completely trash your memory if you do pointers wrong, as it turns out. Leads to seg faults all the time. Okay? All right. So let me show you, see if I can do this here, show you what we've got. All right. OK. So here is our regular old, this is not the first one I showed you. This is a regular old function, right? It's going to say, I'm going to take an integer A and an integer B, and here's what I'm going to do. I'm going to swap them. How do you swap them? Well, I'm going to create a temporary one, and I'm going to say A temp equals that A. That's so that I can now say A equals B and not lose the value of A. And then I say B equals the temporary value. Now, in this function, does that swap A and B? Right? In the function itself, A and B are now swapped. In other words, if I was to print out after this, inside this function, if I was to print out A and B, they would be different. They would be the exact opposite of what they are up here, because I've swapped them. OK. That's what happens inside the function. Remember, though, these are actually copies, and the original program won't get that copy. Here's the other way to do it. It looks exactly the same, except now we've got this, oh, it's a reference to A, and it's a reference to B. Same exact code. Inside the function, you see the changes. Outside the function, you also see the changes. And then finally, now this one looks a little different. This says, all right, give me a pointer to A and a pointer to B. Now, we create our temporary integer. It's not a pointer anymore. It's just a new integer, right? A pointer, or an integer. But we're going to dereference A with this star A. We're saying, go to the address of A and give me that value. And that's going to be temp. And then we're going to say, go to that reference of A, or where A is, and replace that value with whatever B points to, that value. And then we're going to do the same thing with B and temp. We're going to say, now, whatever B is pointing to, set that equal to what temp is equal to. This also changes the value in the calling function. OK? All right. And then I'm going to have my main function. And here's what I'm going to do. I'm going to create two variables, 2 and 5. OK? And I'm going to say what they are. And then I'm going to try to, sorry, it's pretty big font. Then I'm going to actually do the swaps. I'm going to do the swap first with the regular one that hopefully won't work. Well, we hope it won't work because that's the way we know it won't work. Okay? And then the second one we're going to call swap 2 and see what the answers are. And then we're going to do it again with the address of the values. Now, again, these are pointers, and this is saying give me the address. It's different than in the calling, like in the declaration of the function. I apologize for C++ for being that silly to use the same exact reference, same exact character for that. I don't think they should have done that. All right. And then we're going to be done. OK? Let's see what happens when we run this. And the answers are going to be down here. OK? All right. So starts out, my and A is 2 and B is 3. We go through that first function, which is the one that does not pass by reference and does not use pointers. What are the answers when we return, when we're done? They're still 2 and 5. We didn't actually change them. OK? That's the part that will maybe confuse people if they don't know what's going on here. The second one, we use references. The exact same calling syntax, but we use references. And guess what? It does swap them. Okay? And in the third one, I should have reset them, but I didn't. So right now, when I call the third one, A is now 5 and B is 2. So when I swap them back again, it should be the reverse. Right? And that does work. A is now 2 and B is 5. Okay? So 3 different functions that do exactly the same thing, only 2 of which work, and only one of which is particularly clear, which is, I would say, this one. Okay? That's why we use references. Questions on that? Okay? Feel free to download this code off the web page and take a look at it and play around with it if you'd like. See what it's going to do. All right? OK. Good. Good. We're moving right along. OK. Next topic. Remember the other day, we talked about singly linked lists, right? We talked about lists where there's a node, and that node has a pointer to the next item in the list, right? So it goes from I'm one node, and then the next node is the next item, and I can point to that one, and then it goes all the way down the line. We've got 2 special nodes. We've got a head node and a tail node, although we didn't explicitly call it a tail node. And we had it like that. There were some problems with that, though. Not problems, but some inefficiencies with that. Okay? First thing, if you are, let's say you have, let's just use this, so I won't draw another one right now. Let's say you're at this. That's actually not a good thing because it has double links in it. I'll draw it. OK. Here's the one we had on the board the other day. OK, like this. If I am here, how do I get back to this one? Start from the beginning, right? Which isn't too bad for this one, but if I'm somewhere down here and I want to get one back from it, I have to go all the way back to the beginning and go boom, 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 and remember to stop when I get to one that's pointing to the one I was just at. Okay? Not particularly efficient. Not particularly efficient. Okay? So what we can do, and by the way, that's one inefficiency. Another one that just looked a little strange was if I want to remove this node, what node do I need to know about? This one, the one pointing to it. Yeah, I need to know about this one to delete this node. That seems inefficient and seems a little odd. Because if I want to delete this node, I should just be able to delete that node by saying it's gone, right? Because all I need to do that. OK, so what we can do is we can do this thing. And you can see it up here. It's called a doubly linked list. Here's what I'll attempt to do, because somebody told me this was a better idea. This probably isn't going to work. I'm using orange chalk. And then let's see if this is a different color. Can you kind of see a different color there? Well, we'll always try to do reverse pointers in white. This one is going to point back to the previous node. So it's called doubly linked simply because it's linked on both sides. Okay, and I forgot about this one. Right? The tail always points to null. Even the head pointer has a pointer to its previous node, but there is no previous. That should be white. It is the previous, or it does not have a previous node, so that's also going to point to null. Okay? So the nice thing about this is now we can do a few things. The first thing we can do is we can say, if I want to, well, the nicest thing I think is if we want to delete this node, all we need to know about is this node, because we can get from this node to the next one and to the previous one by following this pointer. Okay, so you can do this by both different ways. You can now get this one, and you can get this and this. The problem is reconnecting all the links, right? Okay, so for instance, if I want to delete this node, like this one's going away, right? If I want to get rid of that node, it's going to be gone. In fact, let me just delete it. I mean, let me just erase it, right? It's going to be gone. All right. What do we have to do to the other nodes now? We have to connect them up to the proper place, right? So we need to make sure that this one goes all the way down to there, and this one goes all the way back to there, right? All the way back to here, and gets connected up properly. So there is a little bit more bookkeeping involved. Okay, there's a little bit more bookkeeping, and you have to do that properly so that you know where it is. But you've got all the information you need. Okay, when this one was still here, right, we knew from this one which one this one was and which one this one was, so we can do all the repointing of those pointers correctly. Okay, so far so good? All right. And by the way, we can also go both directions in the list. If we wanted to start at the end, if you wanted to print out a reversed list from a singly linked list, you would have to do the following. You would have to go to the head, go all the way down to the end, print that one. Go back to the head, go all the way to the second to last one, print that one. Go to the head, go all the way down to the, well, at this point it is the head, and print that one. And you've got to like traverse it a number of times. That is like super duper inefficient. Okay? Not the most efficient. If you want to print this one backwards, the doubly linked list backwards, easy. Go to the end, follow, print, and you're done. See how easy that is? Okay, so that's why we would have a doubly linked list like this. Okay, everybody gets that part of it. Let's take a look at how we would change our node in this case. It's actually pretty simple, right? I don't want to belabor the point. The only thing we really need to do to change this node, the set data is going to be the same for our node. The set next, it's going to, instead of last time it was set link, now it's just set next, right? Because it's the next one. We're also going to have a set previous, right? It's on the same line because I ran out of space. Although, yeah. It's called set previous, right? And that sets the node previous to. And the getters are going to be the same thing. You're going to get data, you're going to get previous, and get next. So those are only a couple changes there. And then each node, instead of just having one link, now has two links. All right? Easy enough, I hope. OK. The other day, on Monday, we said we're not going to create a linked list class, right? Well, sorry, forgot about this one. All we need to do now is set both pointers to null when we create the node. I'm going to show you the basics of a linked list class, which is going to have all of the functions in it to work on nodes. It's going to know about nodes, and it's going to be able to add nodes basically to itself. Okay? It's going to have a constructor just like all the classes, right? It's going to have some getters, which are going to get the head and get the tail. Okay. It's going to have a whole bunch of functions here. There's going to be a function called insert after, which means if I want to insert after this node, it's going to put a new node right in the middle here. Okay. Same thing for before. It's exactly analogous. If I want to do before this node, it's going to put a new node right here. Okay. There's also two functions which are very, very similar. In fact, they just call these insert before and insert after on the head and on the tail. So there's an insert at the beginning, right, which puts a new node here. There's going to be insert at end, which puts a new node here. Good? All right. There's also going to be a remove node. This is so nice. We don't need to know anything about previous to this one. That's great. And there's going to be a clear function, which just gets rid of all the nodes. And then we have, this is actually the insert after function, which I'll show you in a second. And then a couple other functions here. Okay, we're also going to be able to do a list search forward, which we said we can go forward, or we can go backwards and go backwards. We're not going to go through all these today. Just going to have these up there for you. You can look. And then finally, we're going to talk about this one. And this is the part that the board was like filled with arrows going everywhere that kind of confused people. So we'll see what we can do better this time. All right. And then finally, the private elements. All the linked list needs to know about really are the head and the tail. I threw in a node count too, because why not? If you want to know how many nodes are in it, keep that around. It's pretty easy to do, right? You need to add one when you insert and then delete one when you remove a node. Easy enough. Okay? All right. Let's take a look at this function. Okay? Let's erase the board and say that we are no nodes yet. Okay? We have just constructed a linked list. Okay? Let's say we've just constructed a linked list, and we've got in our linked list constructor, we say that we have the head pointing to null, and we have the tail also pointing to null, right? Which means that there's no nodes in the linked list yet. Okay, so we've got a head and a tail, and that's it. All right. Let's do this. Let's create a couple of nodes here, inserting after some position. Okay, and we'll walk through this, and you'll see what it actually does. Okay. We are going to insert after the head. Why not? Doesn't really matter. It could have been the tail because they both happen to be null, so it doesn't actually matter. We're going to say insert after a node, and then let's throw a value in there. Let's put 6 in there. Okay, we're going to put 6 in our new node. All right. So first things first. Is the node we passed in null? We're passing in the head. Guess what? It's null. So we got to follow this little part here. If we, well, I'm sorry, I totally missed the first part here. We're going to first create a new node, and then we're going to set the value to 6. OK, so here's our new node. OK, and we're going to create the node, and it's going to be 6. And when we create a new node, we say that the next pointer points to null. And we'll use this one. White will be that, orange will be this. Hopefully, we'll be able to see the difference. The previous pointer will also point to null. Okay? And that's so far so good. If that's the only node that we've created, our head is going to point to that node, and so is our tail, because that's it. Okay? So our head is going to point there. Let's see, we'll do it this way. Our head is going to point there, and our tail is going to point there. Okay? Do we have a proper doubly linked list? We've got a node. It's got pointer, the head node and the tail node both point to null in the correct directions. Right? The tail node points to null next, and the previous node points to null. The head node points to null previous, or points its previous to null, and we're good to go. Okay? Let me stop there for a sec. Questions so far on what's going on here? Yes?
So does the head kind of have like 3 data parts, where before the nodes only had like a head and a tail? Does now it have kind of 3 portions because there's a tail on both sides plus the data?
Well, yes and no. By the way, the node doesn't know anything about the fact that it's a head or not, except that it's got a null pointer in one direction. That's all it knows. the head pointer is pointing to some node, and it happens to be that one. That's all that's going on there. There's no other information. Yes, there's three parts to it, right? There is. There's the data, and then there's a next pointer and a previous pointer. So that's what it's got. Okay? Yes?
Why is head pointing to null, which is pointing to node?
Yeah, that's a good question. Because I didn't, why is head pointer null, which is pointer node? Because I didn't delete the fact that it was pointing there. How's that? Good. Good question. All right. Yes?
Why is head and tail both pointing?
Good question. If you have one node in your list, is it the head of the list? Yeah. Is it the tail of the list? Sure, it's the only one, right? It's the head and the tail in this case. It's one node. So that's why they're both pointing there. Yeah, good. Anything else? All right, I want to take this. Yes?
So if you have empty list, right? So what is bundled there? So what do you pass in that function?
Yeah, I'm passing the head pointer, let's say. That's what I passed in, the head pointer, which was null, correct?
Yeah.
OK, and then the first statement in here after I create the node is that pointer null? That means that I've got an empty list, and so I need to deal with it as a special case.
Oh, so you're just saying that the head is null.
Yeah, the head is null. When we create the list, both the head and the tail point to null because there are no elements in it, no nodes in it. OK, yes?
Why is it that you need to call a node class at the top?
Ah, yes. Yeah, this is confusing a lot of people only because you haven't seen it before. In the node class, we talked about this the other day, in the node class we've got this value type which says what kind of value is a node. I happen to make it an integer in this case. The nice thing with doing it this way is that anytime I want to go change the type of stuff that's in the node, I change it once in the header file and it's done. OK, that's what that's there for. Yeah?
So if you have to pass in a node into this function for it to work, how could it be an empty?
Because I've got this little check right here. Right? A node is this. I'm actually passing a node pointer, which can be pointing to null. Null is a legitimate place for a pointer to point. You'd just better handle it correctly.
So you have to create the null pointer outside of the function?
Yeah, that's already been done. So what happens is when you create a linked list, it says, I'm setting up a linked list. My head, I've got a head and I've got a tail. My head is null and my tail is null. That's it. So there are no nodes yet. But you're right, it's a special case. And you always have to think about those special cases. OK, good. Yes?
What is the node and the arrow to get at the arrow to get previous? What is that line doing?
These ones? OK.
Like the elf, like above or below the end.
Down here, you mean? Yeah, I tell you what. Hold on one sec. When we get there, you'll see what it is. But good question. You'll see what it is. OK. Let's keep going down here, and we'll get to those kinds of questions. OK, but everybody's kind of on the right page as far as what's going on here. We've created one node. We've inserted it. And we're done. And by the way, this is an else. The whole rest of this function is else. So the first one we create, that's the only part that runs. The rest of this doesn't do anything yet. Doesn't do anything yet. OK. Let's add another node. We'll insert another node after this one. OK? Everybody gets what we're going to do? We're going to have one more node, and it's going to be after this one. OK. So we go through our function, and we pass this node pointer to the function. So it's going to know about this. In this case, we could pass the head again, because now the head does point to a node. But we're going to pass a pointer to this node in here. OK, and that's what a node is now going to be. In fact, I could just do this. I could say a node is now pointing to this as well when we start this function. OK, it's just another variable. And that's what it's pointing to. Okay. All right. First thing we do, we create a new node and we set its value. Let's make the value of this one equal to, I don't know, 15. Right? OK. So we're going to create a new node like this. OK. Its value is going to be 15, and it starts out with its tail pointer, or sorry, its next pointer to null, and its previous pointer also to null. Without looking at the code, what do we have to do to make that a linked list now, to make it proper? Yeah?
You gotta set the previous to 26 and the 6 is next to 15.
Yeah. We have to make sure to set this pointer to point to the one that's previous now, And we need to set this pointer to point to this one here. And that's what, hopefully, this code will actually do. OK, let's see if it does it. All right, first of all, is a node pointing to null? No, it's now pointing to some node here. OK, a node is not pointing to null. Then we do this part. So now we get to do this part. OK, we are saying new node set previous to go to the node we're working on. OK, new node, which we just created, we're going to take its previous pointer and we're going to set it to point to the one that's previous to it. Then we're going to say new node set next of the nodes next. So basically we're saying new node, OK, set next of this one to be what this one points to. So there's actually a little bit more than just setting these nodes, because we've got to make everything point to the right place. OK, there could have been another one in here. We're going to do this one more time, and you'll see what happens with that. OK, we'll see what happens with that. OK, but this is to answer your question here. OK, what this is saying is set the next pointer of new node. Isn't that this one? OK. Set that to what a node's next pointer already is pointing to. So this one's pointing to null. We need to set this one to point to null. As it turns out, it already is. But we're going to do it anyway. We're going to erase the null, and then we're going to put this null here, and it's the same thing. But it's going to end up being null. Everybody get that? That's to set this pointer here. OK. Yes?
All
Right.
nulls are the same, so could you also, if something else is already pointing to B was pointing to null?
If something else is pointing to null, yes, you could do that too. We want to make it, the whole point of programs, right, is to make it so that you don't do extra work and you don't try to confuse the whole thing. So yes, in this case, you could say, hey, look, if it's already null, if get next is null, don't do anything. But in this case, we're just going to make it simple. We're just going to say, make it what this one is, make this one what this one is. If it happens to be the same, who cares? OK. All right. So that one's now null. Let's look at the next line. OK. So we did that one. OK. If new node get next, that's this one, that's this pointer right here, is null, where are we? Where does that mean this node has to be? At the tail, right? So we'd better go and update the tail to point appropriately to this one. Okay? So by the way, you'd answered before, you have to set the pointers this one and this one. There's a little more to it too, right? We also have to set this one, and we have to also set the tail or the head or whatever it happens to be. In this case, it's the tail. OK. It was true that our next one was null, so therefore it's the tail. So we don't actually have to do anything to something past here, okay, which we will on the next. Well, we won't on the next one, but you would. If there was another pointer here, right, this one wouldn't be null. So we would need to take this one and make it point back to here, right? Because that's you got to think about all the cases. And one case happens to be if we're inserting after this and there happened to be another one here. We'll do that next. We'll insert after this one and we'll see what happens. Okay? And then, so this isn't even going to happen for this node. But finally, we're going to say, all right, our node that we've been passed in, we've got to set its next to be our new node. And that's going to change this one to point there. All right. Do we have a complete linked list now? Doubly linked list. We've got a head. We've got a tail. We've got a couple nodes in here. The head, its previous points to null, which is good. Its next points to the next node, which is good. We've got another node. Its previous points to the previous node, and its next points off to null because it's the tail. We're good to go? All right, good to go. By the way, one of the reasons I'm kind of hammering away at this is that I heard from the last data structures class that people didn't quite get this stuff after a while, and especially near the final exam. So we'll try to nail it now and then do a couple assignments. Along those lines, the next assignment I'm going to give on Monday, and it'll probably be due the following week, either Monday or Wednesday. And it's going to be involving linked lists, maybe not doubly linked lists, we'll see. But it's also going to be involving dynamic arrays. And I think it'll be kind of cool, actually, kind of a cool project. You guys use the calendar on your phone, right? Either on your phone or like Google Calendar or Android Calendar or whatever, right? Use that to keep your life in order, right? Does anybody here use an actual paper one? There you go, a few people. That's perfectly fine too. That one doesn't need batteries, right? Needs a pencil, but doesn't need batteries. And you can't store that in the cloud, though. So, you know. But anyway, for those of you who do have a calendar, have you ever wondered how the calendar actually stores the data in the calendar? Right? There's a lot of things to think about. Right? You've got to store a date. You've got to store like an event name. You've got to store it in some order such that you can get the list and you can put it on the screen and whatever. We're going to create a couple of data structures that actually allow us to build a little calendar. And then if it works right, we're actually going to have it so that you can use your calendar to export your own Google Calendar stuff into it and stuff, and maybe import. So it'll be kind of fun. Hopefully I think that'll work. It'll be fun. But anyway, point is, all this linked list and dynamic array stuff we're going to use in the next assignment. Okay. All right. Okay. So we said we've got our 2 nodes in here. Let's add a third node. This time we're going to do the same thing. We're going to insert after this node. So it's actually the same thing. We're going to insert after this node, which is exactly what we did before. But now there's another node in there to contend with. Okay? So we're going to pass in, again, this node, like this. And let's see what happens. Okay? What's the first thing we do? Make a new node and set its value. Let's make the value for this one 5. No, 3. Okay? What's your favorite color? Yellow. No, green. You guys know that? You guys know Monty Python, I hope?
Yeah.
It's even before my time, more or less. OK. Anyway, so we're going to make it 3. OK, so you create a new node. OK. Let's create the node. Let's do it right here. It's going to be a little smaller than the other ones, just sort of. OK? All right. Is that all right? It's a little smaller. It's really not smaller. It's just abstractly smaller. OK. So we're going to create a node here. And initially, it's going to be set to null, the next pointer. And the previous pointer is going to be set to null. Right? And I should keep my colors straight. So this one should be this color. OK. All right. And we're going to then set the value to be equal to 3, like that. OK. Let's go through the algorithm here and see if it works. First of all, is the node we passed in null? It is not. It is actually a node. We go down to here. OK, start off. The new node, set its previous to be equal to the one we passed in. All right, let's do it. Its previous goes to here. OK. All right. Next, set the new nodes. OK, the new node, set its next to be equal to what the one we passed in next used to be, or I guess currently is. But this one points to here. Now we need to make this one also point to here, because we're trying to link these up correctly. OK, I mean, it's like what was that game, Red Rover? Remember that game when you were a kid? Red Rover calls somebody over, and then somebody breaks an arm, right? Like, that's all, you know, right? I mean, it's like Red Rover, call the ambulance, right? In this case, you're trying to like take 2 people and link somebody else between them, and you got to link up everybody's arms correctly, right? That's really what's going on here. OK, so we're going to take this one, and we're going to make it equal to what this one pointed to. Well, currently points to. OK, and this one, oh no, did I do my colors wrong? I did. That guy who told me to do colors, he was smart, but I'm not smart enough for it. OK, there we go. All right. So now we have properly linked up this guy. But we've got some other things we need to do. Yes?
So when you made your new node right here with the green and you set its value, it automatically had a header and a tail that were set to null.
It automatically had a next pointer and a previous pointer set to null. Yes, that was what happens in the constructor for that one. OK? All right, good. OK, let's move on. So we've done this, we've done this. OK. if the new node's next is null. Is this one pointing to null? No, it's not. So don't do this. Do this. Now we need to say new node, get its next, right? And then set the, we need to do, this is where it gets a little crazy. Okay. We need to say, what's the new node pointing at? The new node is now pointing here. Set its previous, right, to be the new node. So you got to look at this one, say what's it pointing to? It's pointing to this one. Set its previous, instead of pointing to the old one that was behind it, now to the new one that's behind it. Okay? Oops. All right. Now this is going to point to here. Good? All right. OK, so that was this one. There's one final pointer we need to care about, right? It's the next of the one we passed in, which we set to be the new node that we did, which is this one. We're saying the next of the one we passed in now needs to go to there. Aha! All right. Because it was somewhere in the middle, we didn't need to fool around with heads or tails or anything like that, right? But we did need to make sure that all these pointers, we need to change 1, 2, 3, 4 different pointers to be correct, right? Just so this is the guy that gets his arm broken in Red Rover. Right. Okay. All right. So questions? Yes.
With all this moving the tail business and checking this stuff, would it be a good idea to move back to a help function?
This is our help function, right? So yes. So yeah, I mean, in the sense of doing all this moving, this is about as easy as you're going to get for this function, right? You can't. This one's saying get the next of the previous. You probably could break this up into one other function. I don't know that it would make it even easier though to understand. Good question, but I'm not sure this one leads to any easier behavior. Yes.
Can you just go over that statement again?
This one?
Yeah.
OK. First of all, we check to see if the new node's next pointer is null. So that was this one, which we just set, right? Does it point off to null? It does not. Okay. If it did, that means it's the tail, because the last one. So then we need to deal with it in tail. OK. The else one here is this. We say the new node, its next element, the one it's pointing to, that's this one. We need to set the previous of this one to point back here. So we need to first say, what's this one pointing to? Oh, it's pointing to this one. This one's previous goes to here.
Okay, so that's what does the arrow pointing to the left. Right?
That's this one right here.
Okay.
Yeah, good. Good. All right. Anybody else have any questions on this one? Whew. That was a little. That's a lot of stuff for like, just doing this. But again, the efficiency doesn't come from this, which really isn't that hard. How much moving of nodes did we do? None, right? We didn't have to move any nodes. We just had to move a bunch of pointers, which happens really fast. We didn't have to move memory locations. Okay. All right. And we have analogous functions that add before or insert before. And we have ones that do insert at the beginning and insert at the end, which are identical. It's really the same thing. It just gets called with the head or the tail. OK, that's how you do inserts. Yes?
Why, when you're calling or when you're creating a new node beginning, do you use parenthetical stuff?
Right here? Whenever you do new, that's what happens with new. You do need a parentheses when you use new. That's all. Yep. Yes?
Is there any case when a singly linked list would be more efficient?
Yeah, sure. A singly list linked. When do you think a singly linked list is more efficient? In terms of efficiency, in terms of what? Efficiency in terms of time or memory?
Well, no, I'd say it's more efficient in terms of memory.
OK. Why?
Because each node has to contain less information.
There you go. Yeah.
It has the one after.
Yeah. By the way, you almost never see linked lists with types that are integers, because there's a lot of overhead here, right? You've got to have an integer for this one and this one, and this. So everyone has 3 times as much stuff as it really needs, which is what you're talking about. right, for a doubly linked list. So yeah, so singly linked lists can be more efficient if you have to store smaller types because each one does have extra memory that goes along with it. Good point. There is an efficiency part for the time too, because notice we have to do all this pointer changes, and we have to change this one and this one and this one and this one. Before we only had to change at most 2 pointers. So it was a little more efficient that way. Yeah, the big picture, probably not going to make a big difference. You gain enough from the doubly linked list that you might as well do it that way. For the assignment, like the one coming up, if you don't have to use a doubly linked list, don't, because then you don't have to worry about all the details, right? So that's the other, the hard part is in the details for this one. Yeah.
For enter before, would you make another function like this, or just try and enter after one?
Good question. You would make a new function because the point of, well, I guess you could do this because you have the link to it. You could use this and just say, OK, what am I pointing to before? I'll go and do an insert after that. That's fine too. I think you probably could. It would make this function have one more else statement in it, which makes it a little more verbose and a little slower for all nodes in general. You could do that. You would have to take into consideration the fact that, oh, if you're at the head, there's extra stuff to do, and but like there is no node before it, and so forth. But you could. I guess you could. No, you don't try to minimize it. Don't try to minimize it too much, the amount of code you have to write. Okay. Other questions on this? All right. So let's see. That was we did all that. Oh, right. This is what I'm going to show you guys. Totally, almost forgot about this. When we're doing this stuff, right? A lot of this pointer stuff. Whenever you're dealing with pointers, it can get a little tricky to figure out if you've done something right, right? You end up getting seg faults all over the place, and you end up getting this, you end up having this issue where, oh boy, I have all these seg faults, and I have no idea what I'm doing. Okay, I have no idea where this code is. And you stare at it and then until you go blind, right? What we can do is we can use this program. There's a program that is a debugger, right? You've got bugs in your code, you stick it into a debugger, and hopefully that debugger will tell you where your bugs are. Okay, unfortunately, it never quite ends up that easy, but you can, in general, use this. The debugger that a lot of people use is called GDB, for GNU Debugger, I think it stands for. And it is a text-based debugger, right? You get the text, and you just run your stuff there. And like people who are really good at this stuff do it all, like can use that, and it's good. I struggled using GDB only because there's a pretty good learning curve for it. There is a program called DDD, which is, I think I mentioned it the other day. It is on all the lab computers and on the homework server. And if you're connected to the homework server through an X window session, you can use DDD, and it will be this nice graphical interface. And here's what it is. You open it up, and I'm not going to go through all the details. If you want the details, come to office hours. We'll show you how to use it, right? But what you do is you open up the function that you've compiled with, and you have to compile it with a certain flag. I think it's the -G flag, and you get you get your program here, and you can say, hey, I want to stop at this line, right? I want you to start running my program, but stop at this line, and then tell me everything I want to know about what's going on at that point. The other cool thing is that it puts up here, you can get it so that it puts up here what the variable is and what things are pointing to and all that, right? That's pretty cool, okay? In fact, you can actually drag this. Is actually graphical, so you can drag this along, and you can see I know the font is minuscule up here, but that is a pointer from whatever this is to there, okay? That's kind of cool. I'm going to run through this program, and what we're going to do is we're going to insert something in a linked list, then we're going to print it, then we're going to insert at the beginning. Yeah, we're going to create the list, print it, insert at the beginning, print it, remove node. We're going to do these steps, and you're going to see what happens here in this graphical sense. Okay? All right, first things first. We are on this line. We haven't even created this yet. The program knows that this DLL, which is our doubly linked list, exists, but we haven't called the constructor yet. So when we look at it, this is what it tells us. It gives us this weird, funky looking letter number combination here. That's the address that it's pointing to. Before we even create it, it's pointing to who knows where. Okay? because it's pointing to who knows where, when we go to that location, we have no idea what the head and the tail are pointing to because we haven't even created it yet. So let's create it. Okay? In this debugger, we say run, and then it goes to where we've said stop. You can put a little stop sign there, a little breakpoint we call it. And we'll go here. Now I'm going to hit next, which means go to the next line. Okay? And what it will do is it will create the doubly linked list. Now it's got another location here. Don't worry about what that means. That's just a memory location. Does not matter to you what that means. When you get to 40, maybe it'll matter. Right? That one's not going to matter. But this is what matters. The head is pointing to 0x0. 0x0 stands for a hexadecimal number, base 16, the number 0. So the 0x tells me, oh, it's a hexadecimal number, and the 0 tells me what that value is. It's another pointer. Okay? Again, you don't need to know what it is except to recognize that 0x0 means null. Okay? Because it's 0. And the node count right now, how many nodes do we have? 0. Okay? So far, so good. All right. We're going to go print the list. If I type step up here, it would actually go into this print list and show me each line of print list as we're going on. I'm not going to bore you with that right now. Just know that if I hit next instead, sorry, if I hit step, it would go into there. If I hit next, it will actually go do the print list and then come back. Okay, so let's see if that works. Okay, it's tough to see. Down here, it put bracket, bracket, meaning there's nothing in the list. Empty list. Okay, and now it's on this line. So now we're going to insert at the beginning, and we're going to insert the value 1. Watch what happens when I hit next. Not much will happen yet, but I'll show you in a sec. OK, nothing looked like it happened. It flashed, right? This now, the head is pointing somewhere, and the tail is pointing to that same place. Aha. And what's our node count? 1. Watch what happens when I double click on the head. Oop, there's a little node. Data is 1, which we wanted. Previous is, right now, previous is null, and next is null. Why is previous null and next null? Because it's the only node, right? So its previous doesn't point anywhere, and it's next. Now, if I click on tail, watch what happens. I hope tail will also point there. And this font is so small you probably can't read it. Certainly can't read it on the video. This says head and this says tail, and they are both pointing right there. Wow. Right? Fun. OK. Sorry. Fun in that nerdy, I'm a computer science professor kind of fun. OK. Some of you might find it fun. You should take 40. OK. So, right? That's all right. If you at least you're understanding. OK. So let's do this. OK, we're going to print the list. It does have 1 node, so if we hit print, if we hit next, it should go and print the list, which it did. It said the list has 1 in it, our node 1. OK, now we're going to remove it. All right, we're going to remove it, which I didn't show you the remove, but it's actually pretty simple. OK, and then it says error, can't access memory location null, because it removed it and set head back to null and tail back to null, which is exactly what we wanted to do. OK, and now the node count is back down to 0. All right, we print the list again, and it prints out nothing in the list. We're going to insert at the end, which is the same thing. There's nothing in there, so it's going to insert there. We're going to insert 1 again. OK, and then we get our little node back, and it's our only node. We're going to print it again, and it should print 1 down here, which it does. OK, and then we're going to insert at end the number 2. So after this node, we're going to insert another node. Boom. Aha! Look what happened. We have 2 nodes now. Okay, I'm going to move this one over to here because it's the next one over here. Okay, I'm going to move it down for 1 sec so I can move this guy out of the. Whoops. The only problem with this is that that you have to. I don't know why it's not. I don't know why it's not working. But okay, maybe I'm not going to do that. I'm going to leave it right here. All right. So here's our second node. Now let's see if our pointers are correct. The first node's pointer is to the head, to null, which is what we want, because it's the head. The second node pointer is to something that's 0, 6, 0, 2, 0, 5, 0. Well, let's click on it and see where it points. Oh, it points to this one, right? This guy's previous points back to this one, right? Yeah, that's what I was looking for, that little handle on there. I don't know why I couldn't get that before. All right. So maybe if I click there and get it. Nope, still don't get it. OK, but anyway, now we've got that. We've got the next one pointing to null, the previous pointing here, and there's 2 nodes in here. Aha, we have a doubly linked list. And you can see it graphically, which is cool. Right? All right, let's see. We'll do one more here. We will print the list, and it should print 1, 2, which is what we've got, data 1, data 2. Okay? Insert at the end. We're going to insert after this one, and it'll probably go off the screen. Let's see what happens. There it is. OK, it's off the screen. So let's do this. Let's move this one over to here, and then I'll go off the screen. Ooh, got to go down here too. Thanks for nothing. OK. And there, we'll do it maybe up there so that we can kind of get the idea here like this. OK. All right. So now we have insert at the end. Oh, no. Yeah, this should be like this, and this one should be down here, right? I want to keep it in the order that it should be in, more or less. OK. All right. So is this the tail? Yes, it's the one we just inserted at the end. It looks like its previous points back to this one, right? I don't know what this one is right here. Let's see. Let's see if we can get previous points to that one. OK. The next points off to null. OK. This one's previous points back here, which is what we want. This one's next points down to this one. And we didn't change anything on this one, and we're good to go. Make sense? And look, tail points down to this one down here. OK, head, next node, next node. And if we print the next node, we can do that. If I could keep going here, and the thing would be filled up with boxes, right? But suffice it to say, you can keep doing this and see if your logic in your program makes sense. OK? Questions on that? It's called DDD, and it's kind of cool. Good? All right. All right. So we have about 8 minutes. And here's what I want to do. In the last 8 minutes, well, no. In the last 1 minute, I'm going to show you something else. But for the last 7 minutes, I'm going to show you, OK, what do we have to do? This is what I'm going to call the Google interview part of this stuff. OK? The Google interview part is the following. Remember how I said up here, nope, where'd it go? No, I don't have it in there. There it is. I might not have pointed it out before. I think I did. See this function reverse? This is what I call the Google interview part of the course. If you go to interview at a tech company, let's say, and you want to get a job, and by the way, I don't know if you read yesterday's paper, but there was stuff about computer science in it, the Tufts paper, and it said that like you guys come out of computer science degree and make like $1 billion a year. It's amazing. There's like you guys are like very well respected coming out of Tufts computer science, and you make lots of money if you want. So one of the questions you might get at a tech interview could be, you have a doubly linked list, reverse that list. And what do I mean by reverse the list? Okay, I mean that you're all standing like red rover, right? All the nodes are like this. And everybody has got to swap. Yeah, I see some people going, oh, it's swapping, right? What has to happen is the tail becomes the head becomes the tail, and everybody goes in the right direction with their next and previous pointers in the right direction. Okay? So there's a problem with this, though. Okay? If you try to do that, okay, and you're here like this, if you just try to swap with your neighbor, which is really what you're doing, instead of your next going, or I guess for you guys, your next, instead of going to the next, it's now got to point, it's got to be pointing to the other guy who was the previous to you. You've got to point this one over here, this one over this way, and this one over this way. If you tried to do that, right, you'd end up like losing contact with the appropriate thing. So you have to keep some other stuff in mind when you're doing that. Okay? Yeah, question.
So why can't you just rename your tail the head?
Good question. Let's say we did that. Let's say we just took the head and said, now this is the head and this is the tail, right? This is the tail. What would happen? The head node, its next would point to null. Oh, we're in trouble, all right? Its previous points to this one. That's not a head anymore, right? What's the head node have to point to for its previous? Null, right? The head here points to null. So we would need to change this one and make sure this points to null, right? And this can't point to null anymore. It's got to be the one before it. So the null, instead of pointing to null, the head now points to the next one, which is this one in the order. So really what we're doing is we are basically taking this one, moving it to this side, making this one doing over there, and all the ones in the middle, reversing them as we go. Turns out with a singly linked list, you guys from 50 will appreciate this. A singly linked list, there is a beautiful recursive algorithm to do that, right? It's very easy to do, right? You go in, you get the next pointer, and you flip it, and then you recurse, and you end up doing it one at a time. It's very, very beautiful. Doubly linked lists, not so beautiful, right? There probably is some recursive way to do it, but I don't want to wrap my brain around how to do that right now. Yeah.
Break it recursive into a single linked list and then add the double link back to it.
Yes, you could do that. Sure, you could. That's a good answer. You could say, well, I'm going to just say, the heck with it being a doubly linked list. I'm going to do it as a singly linked list, right? Now, in the interview, you'd get points off for having to go through the list twice. Okay? That's where and you might answer that. You might say, you know what, the easiest thing to do, go through it in the forward direction, flip all the links. Then go in the backward direction, flip all the links, you're good to go. And then they'd say, oh, that's pretty clever. What's the problem with that? And you'd say, the problem with that is that you go through the list twice and it's inefficient. And they'd say, oh, great, what's next? And then you go, oh, well, OK, so now we're going to do it one at a time, right? And the first thing you do, I won't, this is where I got into trouble in the other class, right? I tried to do it and errors were everywhere, right? So we're not going to do that. You can see the code online if you want to look at how I did it. But the bottom line is, you go through each one and you flip the links as appropriate. You go to the next one, flip the links as appropriate, go to the next one, flip all the way down the line. And you only need to do it once through the line. So it's fairly efficient in that sense. Okay, and you can do that. And if you also want, Google recursive singly or recursive linked list reverse, and you can see how the recursive one works too. Okay? All right, I have 1 minute. I'm going to show you the following thing in 1 minute, and it only takes 30 seconds, so you're lucky. We could have linked lists, either singly or doubly linked lists, that are what we call circular linked lists. All that means is that when you get to the last node, instead of pointing off to null, the next or the link in the tail points all the way back to the head. The other thing is that the head, if it's a doubly linked list, points all the way back to the tail for its previous. What does that do for you? It does a couple things for you. First thing it says is if you know any node, you can go in one direction and get to every other node, no matter where in the list you are. You better keep track of which one you started at, otherwise you'll go forever, right? But you don't want to do that. But you can do that in a doubly linked list in either direction. But that's the thing that's good for it. The other one that it's good for, when we get to things called queues, you'll find out that it might be a good idea to implement your list this way. If you have a fixed amount of space, let's say you're implementing this in like an array of some sort. If you have a fixed amount of space, what you can do is, let's say you fill up the list with a bunch of values. If you use the last one, right, and then start using the values up, well, what you can do is you can, and let's say your whole thing is, or you're almost filled or whatever, you can wrap around and put values on the other side. So this can now be your head, and everybody's still good. Then you can just move the head pointer, and like this would be the head, and then everybody's good, and the tail is like the last one before it. So it makes it easier to deal with things that are in a fixed area if you still want to go in one direction through it. Okay, so that's that. Okay, I will see you guys Monday, and if you have any other questions, stop by.